Welcome to our journey into the fascinating world of math in nature. Today, we'll uncover the hidden numerical patterns that shape the natural world around us. From the spirals in a sunflower to the symmetry in a snowflake, nature abounds with examples of mathematical precision. Prepare to see the world through a new lens, where math isn't just numbers on a page, but an integral part of life's blueprint. Math in nature refers to the inherent patterns and constants that can be found all around us in the natural world. These patterns can range from the arrangements of leaves on a stem to the structuring of a spiral galaxy. Each pattern follows specific mathematical principles, showing how deeply interconnected math is with our physical world. Today, we delve into these incredible phenomena and understand their implications. Pi is a widely recognized mathematical constant, roughly equal to 3.14. It represents the ratio of a circle's circumference to its diameter, a relationship that remains constant regardless of the circle's size. Pi not only appears in pure mathematics, but also in the natural design of elements like planets and bubbles, illustrating the circular perfection found in nature. In the natural world, pi manifests in various forms. Take, for instance, the arrangement of seeds in a pinecone. These seeds are distributed in spiral patterns that follow the circle's unique ratio. This alignment allows for maximum efficiency in seed packing, demonstrating nature's inherent mathematical design. Such patterns help these plants optimize their growth and reproduction strategies. If you enjoy this video, don't forget to give it a thumbs up and subscribe to Aesthetic Insights for more. Share your observations of math and nature in the comments below. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, starting from 0 and 1. This sequence materializes in the spiraling patterns of shells and the swirling of galaxies. Nature uses this sequence to organize growth and structure, illustrating the embedded mathematical rules that dictate the arrangement of many biological forms. Trees often exhibit Fibonacci branching patterns, which serve a crucial role in their growth. By following this sequence, trees can optimize the way their branches and leaves spread out, ensuring that each leaf gets sufficient sunlight without shadowing the others. This intelligent design supports efficient photosynthesis, vital for the tree's survival and growth. The golden ratio, about 1.618, is another fascinating mathematical constant. Known for its aesthetically pleasing proportions, this ratio has been employed in art and architecture for centuries. However, its real magic lies in how it appears in nature. From the spirals of shells to the curves of waves, the golden ratio outlines a universal rule for beauty and structure in the natural world. Flowers are perhaps the most delightful illustrations of the golden ratio. The petals of many flowers, like sunflowers and daisies, adhere to this mathematical configuration, arranging themselves in a way that maximizes their exposure to sunlight and pollinators. This natural tactic ensures that each petal receives its share of resources, contributing to the survival and success of the plant. The stripes on a zebra or the spots on a leopard are not just for decoration. They follow mathematical models that researchers are still trying to fully understand. These patterns can be explained by reaction diffusion systems, which are mathematical equations that describe how chemicals reacting and diffusing through space can form patterns. Such natural designs serve various functions, from camouflage to heat regulation. Honeybees demonstrate a remarkable use of geometric efficiency by constructing hexagonal honeycomb patterns. This shape uses the least amount of material to hold the most weight, which is why it's favored by these efficient insects. The precision of these structures not only maximizes space and minimizes material needed, but also plays a crucial role in regulating temperature within the hive. Wave patterns, whether in the ocean, in the air, or through the ground, adhere to mathematical laws governing their speed, wavelength, and frequency. These principles, well known in physics, describe how waves can transfer energy through various mediums. Understanding these patterns not only helps in predicting their behavior, but also in exploring how similar principles apply across different natural phenomena. Symmetry is a pervasive element in nature and is aesthetically and structurally significant. It can be seen in the bilateral symmetry of a human face or the radial symmetry of a starfish. This balance is not merely for beauty. Biological symmetry plays a critical role in evolution and survival, influencing mate selection and feeding behaviors. Each snowflake is a unique crystal that forms when water vapor condenses in cold air. Despite their individual uniqueness, snowflakes often exhibit a six-sided symmetry that results from the molecular structure of water. This hexagonal pattern is yet another example of nature's mathematical rulebook, crafting intricate and beautiful designs. The scutes on a turtle's shell create a tiling pattern that combines strength and functionality. These natural tiles are arranged according to mathematical principles that help distribute stress evenly across the shell. This adaptation not only protects the turtle, but also contributes to the species' longevity by providing an efficient defense mechanism against predators. The winding paths of rivers are guided by principles of fluid dynamics, which are inherently mathematical. These meandering patterns help optimize river flow and sediment transport, influencing the landscape over geological timescales. The study of these patterns provides insights into environmental management and conservation strategies, helping us maintain the delicate balance of our ecosystems. Fractals are complex patterns that repeat at ever smaller scales, known for their never-ending, self-similar character. These patterns, seen in broccoli florets or the jagged contours of mountain ranges, reveal a recursive beauty inherent in nature. Such patterns not only fascinate mathematicians, but also provide insights into the processes governing growth and distribution in the natural world. When we cut through fruits and vegetables, we often find surprising patterns, such as the star inside an apple or the spirals in a cauliflower. These structures are not random, but are dictated by mathematical patterns that optimize nutrient distribution and growth. Such intelligence in natural design often goes unnoticed, but plays a critical role in the survival of these organisms. Spiderwebs are masterpieces of natural engineering. Spiders utilize mathematical principles in web construction, optimizing angles and distances that enhance the web's functionality for catching prey and providing structural stability. The precision of these natural constructions reflects the deep-rooted mathematical instincts found in even the smallest creatures. Today's journey through math and nature reveals the intricacy and beauty of mathematical patterns inherent in the world around us. These patterns are not accidental, but are the result of evolutionary processes that optimize survival, efficiency, and beauty. As we continue to explore and understand these patterns, we gain greater insights into the complexity and interconnectivity of life on Earth. Thank you for joining us in this fascinating exploration of the natural world through the lens of mathematics. See you next time on Aesthetic Insights.